Assalamu alaikum. Welcome, dear students, to our second part in chapter 16, Force and Interaction. By the end of this video, you will be able to determine graphically the resultant of two forces. Let's start by reviewing together the main objectives of the previous video. We have studied that a force is a mechanical action exerted by a body on another one. Forces may set a body in motion, modify the motion of a body, or deform a body. Each force is characterized by its point of application, line of action, direction, and magnitude, and that's why forces are vector quantities represented by vectors. The types of forces are either forces acting from a distance like weight mg, electric force Fe, magnetic force Fm, or contact forces like muscular force F, normal reaction of a support denoted by R or N, friction force Fr, and tension of a string T. Consider an object S subjected to one or several forces. These forces are represented by a free-body force diagram which shows the external forces acting on the system, the object under study. These forces can be replaced by a single force which is the vector sum of all the forces acting on the object. This force have the same effect on the object as all the individual forces acting together. This force is what we call the resultant force Fr or the net force. Then, the resultant force helps in studying the effect of all forces acting on the object. Note that in this part we will consider the object as a particle and we will represent all the forces acting on the object on the same point, which is the center of gravity of the object. Now, how can we represent and characterize the resultant force? When we want to represent the resultant force, we will deal with two different cases: collinear forces, which are the forces acting on the same line of action, and non-collinear forces, those acting on different lines of action. Let's start with the first case, which is to determine the resultant of collinear forces. Consider a man pushing a door with a force F1 and another man pulling the same door with a force F2. Note that the two forces are applied on the same line of action, which is a horizontal line. Also, the forces are applied in the same direction, which is to the right in our case. Then, we will consider a special case of collinear forces, those applied in the same direction. Now, as we've said previously, we consider the door as a particle and we represent the two forces acting on the door on the same point. In this case, since the forces are collinear and having the same direction, then the resultant force will have the same line of action and direction as that of F1 and F2, in our case to the right. And the magnitude of the resultant force will be the sum of the magnitudes of the two forces F1 and F2. In other words, Fr is equal to F1 plus F2 as magnitudes. Now a man pulls the door with a force F1 and another man pulls the same door with a force F2. The two forces are applied on the same line of action, then we are talking about collinear forces, but they have opposite directions. Then we will consider another special case of collinear forces, those applied in opposite directions. Let's represent the two forces acting on the door on the same point. In this case, since the forces are collinear and having opposite directions, then the resultant force will have the same line of action and direction as the force with the greater magnitude. In our case, F1 is greater than F2, and this is shown by the length of the vectors. Then, Fr will be directed to the left as F1. And the magnitudes of the resultant force is the absolute value of the difference in the magnitudes of the two forces F1 and F2. In other words, Fr is equal to the absolute value of F1 minus F2 as magnitudes. Note that if the forces are collinear having opposite directions and equal magnitudes, then these forces are balanced and we say that the object is at equilibrium. In this case, F1 vector is equal to minus F2 vector, which means that the vector sum of these forces is 0. In the other cases where the resultant force is different from 0, then these forces are unbalanced forces. Now let's move to the second case, the case of determining the resultant of non-collinear forces. Two men pulls a mule with two non-collinear forces F1 and F2. F1 and F2 are applied on different lines of action. In which direction do you think will the mule moves? Since the forces are non-collinear, then the mule will neither move in the direction of F1 nor in that of F2. Actually, the mule moves in the direction of the resultant force of F1 and F2. After we represent the forces on the same point and after we trace the movement of the mule, which is along the resultant force Fr, we notice that Fr is the diagonal of the parallelogram whose sides are F1 and F2. Then, to find the magnitude of Fr in the case of non-collinear forces, let's prepare our notebook, a ruler, a protractor, a compass, and a calculator. Now, to find the magnitude of Fr in the case of non-collinear forces, let's consider F1 equal 120 Newton and F2 equal 160 Newton. The first step is to choose a convenient scale to represent F1 and F2. For example, each 1 centimeter corresponds to 40 Newton. This implies that the length of F1 is 3 centimeter and that of F2 is 4 centimeter. Now, using a ruler, trace on the figure on the same point the two forces F1 and F2. This is F1 of length 3 centimeter and this is F2 of length 4 centimeter. Take care for the angle between the two forces F1 and F2. In the second step, you need to complete the parallelogram formed by the sides F1 and F2. Fr represents the diagonal of this parallelogram. You can complete it using a compass. The third step is to measure the length of the resultant force Fr using a ruler. The length is measured to be 6.5 centimeter. Now, to compute the magnitude of the resultant force Fr, you should use the same scale used to represent F1 and F2 by applying the cross multiplication rule. You will obtain that the magnitude of Fr is equal to 116 Newton. Note that in our measurements, you can use the compass to complete the parallelogram and trace the diagonal which corresponds to the resultant force. You should take into consideration the angle between the two vector forces which you draw on your copybook. Your drawing will not be totally accurate, so we accept ±2 mm difference in your answers. Now let's practice by solving the following application. Try to focus on the steps followed by your teacher and try to apply immediately on your copybooks. Consider two forces F1 and F2 acting on a particle at point A. Determine graphically the resultant force of the two forces, given that F1 equal 30 Newton and F2 equal 20 Newton. Note that when you are asked to determine graphically the resultant force, then you need to indicate two main characteristics, which are the magnitude of the resultant force and its direction. Let's start by computing the magnitude of the resultant force. The first step is to use a convenient scale to represent F1 and F2. For example, each 1 centimeter corresponds to 5 Newton. This implies that the length of F1 is equal to 6 centimeter and the length of F2 is equal to 4 centimeter. Now use a ruler to draw F1 and F2, F1 of length 6 centimeter and F2 of length 4 centimeter, but take care to draw F2 making an angle 120 with F1 using a protractor. And here we draw F2 of length 4 centimeter. Now the second step is to complete the parallelogram and trace the diagonal which corresponds to the resultant force. We will use a compass to complete the parallelogram in this way, and then we represent Fr on the figure. Now, the third step is to measure the length of the diagonal formed by F1 and F2 using a ruler. The length is measured to be 5.5 centimeter. After that, you can compute the magnitude of Fr using the same scale. Each 1 centimeter corresponds to 5 Newton, then 5.5 centimeter corresponds to 27.5 Newton. As we've said, to determine graphically the resultant force means that we need to indicate the magnitude and the direction. The magnitude is F equal 27.5 Newton, and the direction, using a protractor, we measure the angle formed by Fr with either F1 or F2. Here, Fr makes an angle approximately 40 degrees with F1. Let's note the following special case of non-collinear forces, where F1 and F2 are perpendicular to each other. Also in this case, Fr is the diagonal of the palm or the rectangle formed by F1 and F2. But to determine the magnitude of the resultant force Fr, you can use Pythagoras theorem, where Fr square is equal to F1 square plus F2 square, which implies that Fr is equal to the radical of F1 square plus F2 square, all of them as magnitudes. Also, to indicate the direction of the resultant force Fr, the resultant force Fr is making an angle alpha with the horizontal or with F1, such that tangent alpha is equal to the magnitude of F2 divided by the magnitude of F1. Now, to summarize the ideas of this video, we have studied that the resultant force Fr is the vector sum of all forces acting on an object. Fr had the same effect as all the forces acting on this object. To determine the resultant force in the case of two collinear forces having the same direction, the magnitude of the resultant force Fr is equal to the sum of magnitudes of the two forces F1 and F2, and Fr vector had the same direction as F1 and F2 vectors. In the case of two collinear forces having opposite directions, the magnitude of Fr is equal to the absolute value of the difference in magnitudes of F1 and F2, and Fr had the same direction as the force with the larger magnitude. In the case of two non-collinear forces, Fr vector represents the diagonal of the parallelogram whose sides are F1 and F2 vectors. This is the end of part 2. Thanks for your attention.